enthalpy. Enthalpy is an example of what's called a state function, and it has the same unit as energy. Okay, and the motivation for defining this, making this up, is because in a lot of situations we deal with processes happening at constant pressure of 1 atmosphere. So the external pressure is 1 atmosphere. We carry out reactions that are open to the atmosphere. Okay, so the pressure of your system then would be constant. It will be equal to the external pressure. So the final pressure and the initial pressure would be the same during the process that we're interested in. Okay, so what if it's constant? Well, going back to the first law, we said delta E, the change in internal energy, is Q plus W, right? And if you recall, we defined W to be negative P external times delta V. So that's your W right there. So you can say then that E final minus initial, that's delta E, is equal to Q, this is Q, minus P, and delta V is V final minus V initial. Okay? I can rearrange this equation to solve for Q. I can see that what happens here. I can move my P times V final over to the left side, and P, since P is the same as P final, I can call that P final instead. So I have E plus P final V final minus E initial, and then P times V initial I can move to the other side as well. So anyway, it should be a simple matter for you, simple algebra to go from this equation right here to this equation over here. You can see here that Q, the amount of heat flow, is just E plus PV in the final state minus E plus PV in the initial state. Okay, since E, P, and V are state functions, they only depend on what your state is, not how you got there. Okay, then that means E plus PV is also a state function. So we're going to call that state function enthalpy, H. So EF plus PF VF is HF, final enthalpy, and the initial enthalpy would be E sub I plus Pi V sub I. So the change in enthalpy then is equal to Q. So although Q, okay, depends on what path you take from the initial state to the final state, for most of the processes we're going to be interested in, which are happening at constant pressure, we can associate Q with a state function, with a change in a state function. So Q in this case would be equal to a change in a state function called enthalpy. And that has some significance, which we're going to talk about later. But basically what we're saying here is we have found a state function that we can readily measure in the lab by simply measuring Q. We already know how to measure Q in the lab, right? We know how to measure heat. Okay, so let's apply that concept to this question right here. The volume of a system changes from 40 liters to 20 liters at a constant external pressure of 2 atmosphere, and this much heat was released, 8.406 times 10 to the 4th joules. What's our Q? 8.406 times 10 to the 4th. That's what Q is. It's the amount of heat released, right? But what's the algebraic sign? Heat is released, so the system is losing energy. So what's the algebraic sign of Q? It's negative, right? By convention, Q is negative if heat is released. What would be our W? What's the formula? Minus P external times delta V, right? And our pressure is constant, so our external pressure is P. It's 2 atmospheres, so negative 2.00 atmospheres. What's our delta V? It went from 40 to 20, so the final volume is 20.0 liter. Initial volume is 40 liters. So our delta V is negative 20, right? So what is negative 2 times negative 20? Positive 40.0 liter atmosphere. Can you change that to joules? What's the conversion factor? 1 liter atmosphere is, just remember, 101 Dalmatians. Okay, so 101.325 joules. Okay, so at liter atmosphere cancels out. 40 times 101.325 is how much? 4,053, 4053 joules. So that's 4.05. I need three, only have 3 sig figs, right? 3 sig figs. So 4.05 times 10 to the third joules. Okay? What's our delta E? First law of thermodynamics says delta E is Q plus W. So what's our Q? Negative 8.406 times 10 to the fourth joules. What's our W? Positive 4.05 times 10 to the third joules. So what would our delta E be? Negative 8.0 something. Negative 8.0, 8.00, okay, 01, okay, times 10 to the fourth joule. Negative 8.001 times 10. Why is that 8? Why do I need 4 sig figs there? That's 8.406 times 10 to the fourth, and the other one is 0.405 times 10 to the fourth. Okay, so your last sig fig would be the third decimal place. If you move the decimal point here, this becomes 10 to the fourth. See? So, all right. So that's your delta E. First of all, let's go back to our formula for W, our calculation of W. Did we have the correct algebraic sign here? Should this be positive? What happened to our system? It shrank, right? From 40 liters to 20 liters. So when it shrinks, you're doing work on it. It will be, you're providing it with energy. You're transferring energy into it. So heat is negative. That means you're dealing with a process where the system lost energy by way of heat, but in this particular case, since it shrunk, it gained energy by way of work. What's our delta H? Constant pressure, so it's just equal to Q. See, delta H is a lot easier to know compared to delta E. If you want to know delta E, you still have to calculate W, but if you want delta H, all you have to do you say that's equal to Q, because this process happens to be occurring at constant pressure. So delta H is equal to Q, which is going to be negative 8.406 times 10 to the fourth joules. It's probably going to be, this type of question is probably one of the easiest ones you'll see on the test. It's really simple. Constant pressure, Q is equal to delta H.